Good.
I don't.
Yes.
Sorry, I don't see this on the derivatives assessment. I just want to make sure that we're all doing the same assignment. It's listed under modules as like deriv assessment.
It's under the big module called Derivatives Skills and Derivative Assessment. It's a separate module. Scroll down to the Skills and Derivatives Assessment.
Yeah. So I see somebody in chat has posted the same number 5 that I have, but that's not what we've just looked at.
We already discussed. I wrote 4 by mistake. It's probably
No,
5.
I just said
Oh,
this is not the same number 5, is what I said. Sorry, I don't understand where the confusion is here. His number 5 isn't the same as like what other people's number 5 is, so I'm trying to make sure he's doing the right assessment.
Yeah, mine's so maybe not. But I'm looking at it. Mine say non-E derivative assessment practice only, Wednesday, August 16, 2020.
oh, so you are working on the WebAssign one, not the form.
Wait, so it's in Canvas or
it's only in Canvas. The derivatives assessment is only in Canvas.
Okay, my bad.
No worries. Okay, good. Other questions for me? Anything else?
Can we look at, I know we've done a lot so far, but can we just look at something to where it's like a power to a power? So I'm looking at number 12 from 3.6.
Yes.
And so that is, it wants to use logarithmic differentiation to find the derivative. And the function is y equals the square root of x to 3x to the power of 3x.
Is this a homework issue problem?
Sorry, this is from WebAssign.
Oh, perfect. Awesome. Okay. So first of all, we have natural log y, which is 3x times natural log of the square root of x. Is this step okay?
Yes.
Perfect. So now we're differentiating both sides. So this is 1 over y dy over dx equals. The first function prime is 3 times natural log of the square root of x plus 3x times natural log prime times the square root of x prime. So 1 over y dy over dx, this is the product rule. 3x prime is 3 times natural log plus 3x times natural log prime, which is 1 over this, times the inner function prime, which is 1 over 2 the square root of x. Are these steps okay? When you say it's okay, I'll continue, because it's not finished.
Yes.
All of them? Everyone?
Yes.
Okay, perfect. So now the next step would be, I'm on page 5. So here I have dy over dx. I have to multiply by y, but this is y, the square root of x raised to 3x. And now let's see what we can do here. So this is definitely this. This product is 2x, but you will simplify with this x. So I have just plus 3 halves. So 3 over 2, the square root of x times the square root of x in the denominator will cancel with the x from the numerator. And this is final.
Okay.
So one more time. This is 3x over 2x. So the x's go away, so that's how I get only 3 halves. Very good example. Very good. Perfect. That's the only way. If you work on these problems before class so we can make even more progress in class. That's awesome. Anyone else has anything else for us? Anything from anything? Okay, then. You can always stop me if you remember something. So let's go back to that 3. I have no idea what this is. I meant to say 3.10. Probably I meant to start with chapter 3, section 10. I'm not sure. Okay, it's gone. Okay, so we are still talking about differentials. And what is this? It's an application. So the entire chapter 3 deals with applications of integration. Applications. We didn't get to the application because I have to explain what this means, and then we'll get to applications to see where differentials are applied and what's the purpose of this. So let's go back to that graph. First, I need to explain what they mean and how we determine them. So here's a point P. Of course, there is a point very close to it because all we are interested in is the slope of this tangent, right? The rate of change at this point. So that's the whole purpose. But we are expanding now. So Q is very close. I'm zooming in. So here's Q. And this is X. This should normally be X plus H. But we're not going to use this notation now. We're going to use X plus dx or X plus delta X. And I was explaining, yes, this is delta and this is also delta. This is lowercase, this is uppercase. Okay. Of course, we know that this is f of x because this is function f of x. And of course, we know up here we have f of x plus dx, which is the same with f of x plus delta x. How come? Well, the error is this. Minor change or error. I don't know how you want to call it. It's the same. Minor change in x. From x to x plus a little bit. Or error in x. Or delta x or dx. They all mean the same thing. Then we created a right triangle here by drawing the secant line. And we said, well, if there is this minor change, again, this is very small, but I'm zooming in, otherwise I can't explain what's going on here. So for this minor change in x, or this minor change in x, triggers this change in y. From f of x to f of x plus a little bit. This is that called delta y, okay? The exact change, exact error if you want, or change in y value created by an error in x. So see if there is no error, then when x is x, then I get the function value, okay? So if I have a disk and I measure the radius, and if the radius is correct, then the area is correct. But if the radius has a tiny error of delta r, then the entire area will have an error of delta r in it. So it will not be exactly the area that I wanted because there is an error in the radius that will trigger an error in the area. So this is the exact. Okay, now if we create the tangent, if we determine or draw the tangent line at P, and then extend it and extend it and extend it, and then we extend this piece, the vertical line here, we create a right triangle. And it happens that this piece is also the error created by this, but it's the so-called dy. It's the differential because it's determined using the slope of the tangent line, which includes the derivative. It's not the exact error. It's close, very close, but not exact. We always prefer this over this. This quantity will always be easy to determine. This will be more difficult to determine. So delta y, which is f of x plus delta x minus f of x. What is delta y? This piece minus this piece. That's the delta y. This minus this is the exact change or error. in y. The dy is the approximate change using the derivative. So this is the differential of y using the derivative. In other words, and this is approximate. It's not the exact. I'll say not exact. This is exact. This is an approximation of the exact error or change in the y value. Okay, where are we going with this? Okay, we will write exactly what we just said. dy is approximately, I'm sorry, delta y is approximately dy. Now, before I continue here, I need a very important note. Dy over dx is the same with f prime of x. Can anyone solve for dy for us? Can anyone solve this equation for dy? And I will write it here. Can anyone solve this equation for dy?
It's just f prime of x dx.
Perfect. Thank you so much. So this is what I need to replace dy by. And we know delta y is f of x plus dx minus f of x, which will be approximately f prime of x dx. This is a very important relationship, and I'll show you a few examples and where we're getting what is this important for. Not before, I'm going to move f of x to the other side. Notice that we are not putting the equal symbol here. This is the approximate symbol. So then f of x plus dx is approximately f of x plus f prime of x dx. Super important, very, very important concept or result. Here's one application of this. And I would like us to look at it. Where is my class? Who knows where my class is? Oh, of course. What a surprise. Look at that. I'm logged out. I was longing for that. Was waiting impatiently to be logged out. Sorry, I have to authenticate. In the middle of the class and in the middle of Canvas and in Zoom, I have to authenticate. Okay. Okay. Okay, I'm getting an error. I can't authenticate. It's sad and funny at the same time, isn't it?